relay that is used to delay either the opening or closing or contacts for a circuit. It's really a clock. So some of those contacts are designed to operate at a preset time interval, like 1 second, 2 seconds, 5 seconds, 10 seconds, after the call is energized or de-energized, right? And so from there comes the idea of what's called timer on delays and timer off delays, right? There's a few other ones that have appeared as we have software that is able to do that. So you still actually can use these devices. These are mechanical or electromechanical relays that do timing functions. So here's a on delay pneumatic timer. So this guy actually uses air, right? So you have an instantaneous contact that changes state as soon as the timer call is powered. And you have the coil, just like any other relay. You have the normally open terminals. You have the instantaneous contact, and you have the normally closed contacts. And of course, that will change behavior, when you connect them. So they change state. And then you have a normally open terminal, and you have a normally closed terminal. And then you have the ability to adjust the time, like a little delay element on that. So that's an on delay pneumatic type of or air timer, as it's called. All right, they're used for on delay timer contacts. On delay provides time delay when the relay call is energized. In other words, it's energized for a period of time. Right, so you have the normally open time contact close. So the contact's open when relay call is de-energized. When the relay call is energized, there is a time delay in closing. And then you also have the counterpart, which is normally closed. So in both cases, you turn on the device and the device goes on for as long as you have set the device, right? 1 second, 2 seconds, whatever that might be. All right, this is the off delay, right? So the off delay provides time delay when the relay coil is de-energized. So it does the opposite, right? Off delay. I'm going to talk about a few applications, but again, it's got the same idea, normally closed and normally open off delay contact. So there's actually two already we talked about, on delay and off delay timers. All right, so here's an example. Sometimes they refer as the DOE, which stands for delay on energized. And so that particular timer, right, goes from with S1 being the enable. So you enable that and it goes for 10 seconds. And after 10 seconds, then the element that you want to enable or activate goes on, right? So that's an on delay timer. You wait for 30 seconds for something to occur. Okay, that's how that works. Here is a normally closed time open contact. So the idea here is something is already on, and then you enable that timer, and after the time expires, you want the system to be off, right? Because of normally closed contact situation. So that contact's going to open as time expires. All right, then we have the counterpart, which is the off delay timer, sometimes referred as the DOD, okay, which stands for delay on de-energized. And so we have S1, which enables, TD, which is the off delay timer coil, is energized, and TD contact close instantly to switch light on, right? And so when S1 is open, TD coil is energized, and the timing starts after the 10 seconds TDI contacts open the switch, and then the light is off. So they do a little of the opposite function. Here's an example of an off delay timer with a normally closed close contact. Again, the S1 is removed, and at that time, then the off delay timer goes on, and at the 10 seconds being off, then the output event is triggered. So two types of timer, right? On delay and off delay. That's two of the many types. This is how it used to look. The look of the way we program timers today is a little bit different than this, but the principles are the same. So the most common PLC timer. Now, one of the advantages of today's software is that you can actually tweak these timers to do a few other things other than what they're preset to do. But you still have the on delay timer, the off delay timer, and the third one will be the retentive timer on. Not all timers have the ability to retain the time, right? And this is kind of a neat feature. What happens with a tone and a TOF is that they're set for a certain time, right? You cannot alter that. You put it on to 10 seconds or 20 seconds, whatever it might be. But if something happens in between that period of time, the timer doesn't have memory to remember that you had it on for 5 seconds, right? So you want something better than that, and that's the reason why we now have RTOs, which are retentive timers. A good application that is very common, actually, for use of retentive timers is timing the work cycle of a machine, right? So engineering maintenance personnel will want to maintain, or provide service to a machine, and the original equipment manufacturer have decided that every 1,000 hours, right, you need to maintain the machine, whatever, calibrate, lubricate, change parts. And so an RT timer is a good example of that. In the old days, when I was a tech person way back in Pepsi, before I got my degree, actually, it was a tedious task to maintain equipment because you had to have logs and stuff like that, right? Now there is software, and in the case of automated machines, it's a bit easier because that's something that you incorporate in a program. How many hours the machine has worked, right? And the days before, you just estimated because you didn't have a way to control the true hours of work of the machine. So that's an example of RTOs. Quantities associated with timer instructions. You have a preset time, right? And that's the duration for the timer circuit. You have an accumulated time, and that's the amount of time that has elapsed from the moment the timing started. And then you have a time base, which is the interval that the timer times out. If you had a 1/10 of a second for a time base and 50 for the preset time, the timer then will be on for 5 seconds, right? So those are part of the settings that you have to set on. It used to be that you had to set on. They're a little bit different, but you still are going to have preset, accumulated, and time base of some sort. Call formatted timer instructions. So here is a call formatted timer instruction, which tells you the type of timer, right? And we already know there's 3 of them, tone, TOF, and RTO, right? Then they need a label or address, and they also need a timer preset value, right? They also need an accumulated, and they need a time base. So all of those parameters are set when you set your timer. There's a generic block formatted retentive timer, which is more like what they look today. You have a control line and you have reset line. Control line is what triggers the timer. Reset line is what you use to reset the timer, right? Clear off the timer. And then you have the output line, which is what enables whatever event you want to do. Turn on, turn off, keep going, or whatever. All right, on delay timer is used when you want a time delay to occur before an instruction becomes true. So we've said that. And so the run condition is false, and then it goes through. Then you have a time period on delay time duration, and then at that time, after the time expires, you want something to go through. Okay, so that's the on delay timer. Here's the Allen Bradley Slick 500 timer file. Again, there is already two versions before the software we're using now. So Slick 500 is an older version, oldest I will say, and then Slick 5000, actually MicroLogic 5000 is the older one, and then we have of course CCW. Again, this is what I explained at the beginning, so I'm not gonna do a lot of time. Timer tables, it's what used to be used to look at the words and bits associated with the timer. Notice here that this timer table has the name of the timer, T42, right? You can create infinite number of timers virtually. And then you have the enable bit, then you have the timer timing bit, then you have the done bit, you have the preset and the accumulator, right? We'll talk about those. And so they're all there. And this can be, manually altered or modified. So enable bit is true whenever the time instruction is true, right? Timer bit is true whenever the accumulated value of the timer is changing or timing going, right? The done bit changes state whenever the accumulated value reaches the preset value. Its state depends on the time of timer being used. So that's the done bit, kind of an important bit actually. The done bit is where you connect things that you want to enable or disable with a timer. Then you got the preset value, we said about that, which is a word base. That's the set point for the timer, the value up to which the timer will time. And then you have the accumulated, and then you have the actual. So again, as we program timers, they're going to look not exactly like this, but they will have the same principle of operation, right? They might look a little different, but at the same time, you have to keep into account all these bits and word elements. Here is a on delay timer instruction. Timer number is T40. That's the file for timer 0 in that file. Time base is 1, right? So 1 seconds. Preset value is 15 and accumulated value is 0. So again, you're going to have the same things except that the graphic or the command, the icon or the object may look a little bit different, right? As you do your prompts. There you go. This is another version of software that was used not too long ago. As a matter of fact, many companies still using ControlLogic 5000. For whatever reason, they cannot just move on to the newest software and hardware. But there's a timer, and it's got a timer tag name, and it's got the preset accumulated. It's got the enable done bit, and so forth. So that's a little bit of different instructions. So this is an example of an on delay timer program. You already identify the timer name, the time base, the preset accumulated. And again, notice that the enable bit is what connects the output of that timer to time the task that you want to task. Also notice here that actually we're using virtual instructions like T40. That's a examining close contact that is going to be powered by the enable bit, right? And then we have here another examining close contact that will be powered by timer timing. And then the done bit. Okay, so how can we read it? Well, output B will energize at the moment, right, that the timer is turned on, right? Output B is going to energize. Output C will be energized for as long as the timing is timing, right? And output D will become on when the timer is done timing, right? So that's how you can read that. Timing on delay TON, instruction on and off. And what's happening, each one of the bits affected in the program operation, like the case of the tone instruction off, enable bit is 0, timer timing is 0, don't bit 0, it's not accumulated, right? Timer is off. While the tone is on, you need an enable bit 1, timer timing 1, don't bit's not done yet, and it is accumulating, right? When the timer times out, accumulated equals preset, you're still gonna have an enable bit that you need to have. Timer timing will be 0 at that time. Don't bit will be 1, and it's no longer accumulating, right? So instruction off after timeout, everything will go back to normal, like it started, and we reset. So that's how that timer works. Excuse me. I feel like I need to sneeze a little bit. Sorry about that. Okay, so let's move on and look at this example of a timer using Logix Pro. So there's a timer timing. You recognize the bits and words on the timer, and notice the outputs, how they react. Yes, sir.
So, like with these timers, is there a way to set it to where like it happens at like a recurring time every day? So like 8 o'clock in the morning, it starts for this amount of time and then stops, and then like on a loop.
Sure. I believe so. Let's see. So yeah, there used to be a kind of a lab that we did when I taught somewhere else, where we used timers to create a clock. You definitely can create a clock with timers, right? And for that, we're going to talk about that. You use the same concept that makes a regular clock, right? You use cascaded timers. So you will need a timer that will count the second, right? 60 seconds. And then that timer will feed a second timer that will count the minute, right? So when the first timer counts 60 seconds, the second timer counts 1 minute. And so when the second timer counts 60 minutes, the third timer will count an hour, right? And so forth. So you actually can cascade these timers to be able to do a clock cycle function. But there is a simpler way to accomplish something like that, and we haven't talked about it yet, but it's what's called the retentive timer. And that's what mostly I've seen on programs, ladder programs, that will want to count, say, the number of hours of operation of a certain piece of equipment, right? So you don't have to get yourself too complicated. You just basically use a timer that has the ability to count. However, there might be a time limit count that a timer can have, right? So in that instance, you have to create an application with timers. Good question. All right, instantaneous constant instruction from using an internal reference relay. So there is one using a electromechanical type of timer. TD stands for time delay. TD1, that's an auxiliary contact of that time delay, right? And then TD2 is the actual enablement of that. So down below, we have the equivalent PLC program with a timer. So that's a little example. Let's see what we got here. So that's a timing event. You want to run the motor after 50 seconds. Another good application that I can think of timers is sequencing the startup of an operation. again, in my early career, I remember that a particular company I worked for had to set up some giant, what they call compensation benches, I want to say. But the idea is every time you have heavy loads that are gonna, consume a lot of power at the start, you need somehow a way to compensate that. So in the old days, what they used to do is they'll have this giant um, capacitors, if you will, that will be there for when 20 operators will put their hands on the control, right? And 20, 100, 200 HP motors will crank up, right? So that was an awful moment. Okay, so with controls like this, one of the things that have come out, and I have seen it also, is that now you can sequence, right? Even if those 20 operators will push start, a PLC will be able to control and say, we're not going to do that. We're going to kill, the power income here, but we're going to let, two motors start at a time. So when those 20 operators, do that, two motors will crank up, and then wait for however seconds you're programming the control, 5 seconds, 10 seconds, then the second two motors, and so on and so forth. So now companies don't have to be worried too much about investing in what's called those compensation benches. If you're electrical, that will be an area that I think there's still some places where they might have those compensation benches. And there are certain industries where, that's still the case. Not all industries are automated. And so they still use various kinds of methods to compensate for starting up an operation and not having to burn everything. Yes, sir.
At the at the coal mine, they use those a lot.
There you go. Exactly. That's a prime example of that.
Because they're the previous belt, the one in front of it had to be running for a certain amount of time before the one behind
Yes.
it would start, or else it would like overfill.
Exactly. And that's another reason why, right? You want to create a sequence so that your last conveyor doesn't have to be running until load gets to that conveyor. And so we're gonna do some examples and some labs that will give you some ideas on how that works. Conveyor warning signal. So there's the hardware relay circuit, and talking about the devil, right? This is an example of a system that uses a timer to signal a conveyor running. Okay, let's see it in action. It's going to time for 100 units of time, and then the horn will go off. All right, automatic sequential motor control system. I got ahead of myself. This is pretty much what I was talking about. M1 is energized when PV2, right? PV2 is momentarily actuated. So M1 will be energized. When the lube oil pump pressure switch PS1 closes, this guy right here, M2 and TD are energized to start M2 and begin the TD time delay. That's the second rung. After the time delay period of 15 seconds, which is that how it's set, TD1 contact closes to energize M3. So a sequence of motor starting. And this is how it look in ladder. You have PV1, PV2, PS1, and the sequence that's gonna follow, right? So N1 energizes, then PS1 goes in, energizes M2. There's a timer set to 15 seconds before M3 can turn on. 150 units of time. That's about 15 seconds. All right, the off delay timer, I mean, it's just a timer that does the opposite. It's called the TOF, TOF. Start timing instruction goes from on to off or from true to false. So S1 is the input enable bit for that off delay timer, and then is on and then goes off. At the moment that goes off, the timer timing bit goes on, and it's going to stay on for the preset time, right? That means that the dawn bit will go on until that time expires and then goes off. It does the opposite, right? While the on delay timer times the event while the timer is on, this one times the event while the timer is off, right? Going from false to true. Off delay timer, here's an example of that. Okay, when the switch is first closed, the lamp is switched on, right? When the switch is open, timing begins and the lamp switches off after the 15-second delay. If logic continuity is gained before the timer is timed out, the accumulated time is reset to 0. In other words, on delay timers and off delay timers do not have retentive capacity. Okay, so here's an example. Light is on, signal is removed, time off is going until the expiration of the set time. That's what's called off delay timer, right? Because it's off and then starts timing. Okay. Program for switching motors off at 5-second intervals. That's part of the conversation that we were having, right? And you guys are gonna do some of this in your labs. All right, so we have off delay timers because we wanna delay the starting of those motors. So the switch starts the process, and then observe that we're using the dawn bits of those timers here, right? From the first off delay timer, we're using the dawn bit to enable M1. From the second off delay timer, we're using the dawn bit to energize M2. And from the third off delay timer, we're using the dawn bit to energize motor 3. Right, timer off delay table. TOF instruction on, you're gonna have the enable bit on, timer time, the bit will be 0, dawn bit will be 1, accumulated nothing. TOF instruction off, the enable bit will be off, timer will be 1, dawn bit will be 1, and it's accumulated. Timeout accumulate equals preset, enable bit 0, timer timing 0, dawn bit 0. It's not accumulated. And then the off after timeout, you're gonna have enable bit on, timer timing no longer, and dawn bit 1, and then goes back to reset. So it's exactly the opposite of the on delay timer. So here it is. Energize. Everything is completely energized at the moment. Then everything's gonna be turned off at the preset time. There you go. First one. Second one, and third one. So this is an off delay timer to turn off a sequence of motors in sequence, right? Here's a hardware off delay timer relay circuit with both instantaneous and time contacts. So TD is the electromechanical timer, and TD1 is the auxiliary contact, right? So same idea.